Welcome back, students. Last time we discussed somehow magnetic properties of actinides and magnetic properties of lanthanides. You are already familiar with the properties that the magnetic properties were because of two characteristics. One was the spin contribution, and the other one was orbital contribution. In both the cases, spin and orbits are involved in magnetic properties, and we discussed that simple formula which was used for the calculating calculating the magnetic properties of other species was not applicable here for F block elements. Now, majorly we are comparing lanthanides and actinides. So in lanthanides, where 4F is anti-penultimate subshell, and in actinides, 5F is the anti-penultimate subshell. So if we compare the resultant shielding of these electrons in 4F and 5F subshells, so 5F electrons are less effectively shielded as compared to 4F electrons, and this less effective shielding cause quenching of orbital contribution in magnetic properties. So when we are observing experimentally magnetic properties of actinide series, so the resultant value will be less as compared to lanthanides because of less orbital contribution, while this orbital contribution was active in case of 4F series, which is lanthanide series. Coming towards some exact examples, and in this case we will be able to understand the phenomena of quenching of orbital contribution for those systems where same number of electrons exist in 5F and 4F levels, and those systems where same number of electrons are there in anti-penultimate sub-energy level, they are called isoelectronic systems. So Neptunium plus 6 is isoelectronic to cerium plus 3 because both of them possess same number of electrons in 4F and 5F subshells, which are anti-penultimate in both the cases. If we compare the magnetic properties of both these systems, so theoretically we will get the same values for F1 systems, but experimentally the magnetic properties of 5F are less than for F system because of this phenomena which is called orbital quenching. Yeah, quenching of orbital contribution. Another isoelectronic system is Neptunium in plus 5 oxidation state and plus praseodymium in plus 3 oxidation state. Both possess same number of electrons. They are isoelectronic to each other, and the magnetic properties in case of Neptunium, which belongs to actinide series, then praseodymium, which belongs to lanthanide series, are less, and in this case the magnetic properties are more. Third system is Neptunium plus 4 and neodymium plus 3. This is actinide and this one is lanthanide. Both are isoelectronic on the basis of electrons in their valence in their antipenultimate subshell, and the properties magnetic properties of actinide member, they are less as compared to the respective member in lanthanide, which possess the same number of electrons. Regarding reducing power of actinides, so their electrode potential is relatively high as compared to lanthanides, and whenever the electrode potential values are high, so this value make them more reactive, and on the basis of this reactivity they are strong reducing agent as compared to lanthanides. Their reactivity is also high, and on the basis of high reactivity they can react with oxygen, halogens, and some acids in the same way as lanthanides do, but the only difference between reactivity of lanthanides and actinides would be their rate of reaction. So the rate of reaction will be higher in case of actinides, and rate will be lower, or reaction will be slow for lanthanide series, although reaction products will be same if we represent them by a general chemical formula. Next is color of actinides, and if you remember, we discussed color of actinides for color of lanthanides and even color of D block elements. So in case of D block elements, the color was because of DD transition. In case of lanthanides, the color was because of FF transition, and in this case in actinides also the color is because of FF transition because they are F block elements. And this why the color is because of FF transition. This also you know that whenever ligand approaches metal center, so the F lobes are differently affected because the directionality of the ligand will be different. So those orbitals which come in direct contact with the orbitals or with the lobes where electrons are there are where the orbitals are empty, so they will affect more, their energy will increase, and those which do not come in direct contact with the ligand, their energy will resultantly decrease. And this is because of the reason that law of conservation of energy would be followed by the system, would be obeyed by the system, that increase in energy will be equal to decrease in energy. So some orbitals will increase in energy and energy of some orbital will decrease. And between these two or more than two levels, electronic excitation will occur, and this electronic excitation can give various colors to the system depending upon the nature of the system and number of electrons in FF levels or F sub levels, subshell. Now coming toward exact examples, so actinium is in plus 3 oxidation state. We have to discuss these five representative metals. In plus 3 oxidation state, there are no electrons in 5F subshell of actinium, and the system is colorless. Since there are no electrons in order to excite between two levels, therefore the system will be colorless. For uranium, there are three electrons, and now excitation and de-excitation is possible. Energy in the UV visible region will get absorbed by the system, and this energy or this wavelength which has been absorbed or emitted by the system will impart color to the system, and that would be red. For neptunium, where there are four electrons in the antipenultimate subshell, so the color is blue. For plutonium, again the FF transition is possible because of five electrons in F subshell, and color is blue to violet. For americium, there are six electrons, again electronic excitation within different levels is possible, and the color is pink. Coming toward metal in plus 4 oxidation state, so these are representative examples of plus 4 species. So thorium in plus 4 oxidation state is colorless because there are no electrons to be excited within F levels. Protactinium is F1 system, and just like in lanthanide series, F1 was colorless there, so it is also colorless in case of actinides. No color can be observed. Uranium in plus 2 state is green. In plus 4 oxidation state, it possesses two electrons in F level and it is green. And if you compare the color of uranium in plus 3 oxidation state and uranium in plus 4 oxidation state, so here the color was red, and in case of plus 4 the color is green. So even a single electron can drastically change the color of two species from red to green in case of the same complex, even if rest of the environment is exactly identical. So electrons has to be electron in the antipenultimate shell has to be considered for explaining color of different species. Neptunium in plus 4 oxidation state, it possesses plus 3 electrons, and the color is yellow green because the FF transition is possible in the system. And if you compare Neptunium plus 3 with Neptunium plus 4, so here the color was blue and here it is yellow. For plutonium plus 4 the color is orange, and for plutonium plus 3 the color is blue. Here 5 electrons are available for excitation or transition, and here only 4 electrons are available for transition between two or more than two F levels, so the color is orange. For americium and plus 4 oxidation state, again there are 5 electrons and the color is rose. So complete series cannot be discussed here because of the reason that rest of the elements, they are either toxic, they are not naturally occurring species, they are synthetic species. So for synthetic species, on the basis of their radioactive nature, their reactivity, their properties cannot be explained or cannot be explored in full detail, therefore they have not been considered in this table. We already know that only five representative elements of the series on left hand side, they are naturally occurring. rest are synthetic and their half-life is too less, so therefore they are not naturally occurring. And there was another reason that since they are radioactive, therefore they are toxic to human beings and even all living beings. Therefore, their study was not possible in full detail as we have complete data for lanthanide species. Then reactivity of these complexes for these metals for complex formation. So these metals, they have greater tendency to form complexes, and a little bit earlier we discussed that they have greater reduction potential or greater tendency to react with other species, with halides, with acids, and so on. So they also possess some tendency. They also have tendency to make complexes as D block and other F block elements do. And this tendency is greater if we compare mutually the F block elements, lanthanides and actinides. And the greater tendency is because of higher nuclear charge, and this higher nuclear charge results in smaller size of the respective ion. And whenever an ion possesses smaller size, so smaller size make them more reactive, and this smaller size is the reason to explain the high reactivity of these species. So if we compare the reactivity, nuclear charge, and size of these species, so they are more reactive than lanthanide series. Now, small and high charge ions, for example, plus 4, they exhibit greater tendency toward complex formation. And plutonium is a specific example which afford anionic complexes. And this anionic complex formation was the only characteristic of actinide series, which was not determined or which was not observed for actinide complexes. So actinide halides, they make adducts, while lanthanide halides, they were not able to make adducts with alkali metal halides. This is a general example where thorium plus 4 chloride, this has been has been treated with metal chloride, and now this metal chloride in moles of the salt, where this M represents the alkali metals. So N mole N can vary from 1 to onward whenever they react with thorium chloride. So this is the complex, and in this complex, if you think that coordination sphere of thorium in this case is a reactant, it is 4, and coordination number of thorium becomes 5 in this case. So coordination sphere of thorium expands from plus 4 to plus 5, and further another molar amount of another mole of this metal chloride salt can react with thorium chloride. So 1 mole can react, 2 moles can react, and in case of 2 moles, this will be the resultant complex where the coordination number of thorium further extends to 6. So 3 moles of the metal salts can also be treated with thorium chloride, and upon treatment or upon reaction, the coordination sphere of thorium further extends from plus 4 in starting material to plus 7. So there are a lot of chances, depending upon the reaction medium, the amount of this metal chloride treated with thorium, we can observe different products. So can be 5 coordinated thorium, product containing 6 coordinated thorium, and product containing 7 coordinated thorium can be observed for these systems. And the number of products with the same species in the same reaction, it means that these species are more reactive than lanthanides or any other species where single product can be obtained. Thorium chloride and bromide, they form adducts with as monopyridine complexes. Whenever they react with pyridine, wherever they come in contact with pyridine, so only one pyridine molecule can be accommodated by thorium chloride or thorium 4 bromide. Uh, they form complexes with EDTA and acetyl acetonate species, which we will discuss in next slide. The uranium oxide, which is an oxycation, and this was the only characteristic of actinide series, they form unstable complexes with EDTA because most of reactivity has been utilized for formation of this oxycation species. So